Simon, can you sort out this camera because it keeps drifting downwards?
In a second.
Cool.
Where is the drift? Is it in that?
So it's in the vertical. So that's it's that it's this thing. Just give me some in there. Yeah, we got. It's only just top.
Has that? That's on as tight as. That's slightly better, isn't it? No.
Okay, that's fine. Support the camera. I'm just going to move the tripod up a bit.
Oh yes. Do you want me to? How do you want me to line the shot?
So.
With the slide?
Yeah, with the slide.
We have 92 minutes, by the way.
That's fine.
I'll stay this side.
But it's still
drifting. It's not that. Is that just that? Is the camera too far forward?
maybe.
That seems better.
Still drifting slightly.
The talks.
Okay.
I should grab my camera as well. Do you think I've got a minute before the talk?
And is it?
It's in my bag over there. Have I got a minute?
We should start now, really.
Is that okay?
Alright, so thank you all for coming to the second talk about DevRoom today. My name is Simon Hollis. I'm going to talk to you about how to measure the energy consumption of electronics. I'm going to focus on small embedded systems, but everything I say will apply to measuring big devices, data centers, as well as it applies to small devices, like the boards that we have here. So we're going to go through some fundamentals about what you need to know if you want to accurately measure energy consumption, and we're going to then show how you can build up things like what we've got on display at the workshop later on, these homemade, home-brewed, energy-efficient energy measurement devices. They're very cheap, very simple. You've just got to get the design right. Okay. So, what I'll do, I'll give credit to some of the slides here to James, who's at the back of the room. He's going to give me a few graphs to include. And my presentation is running away with me already.
No credits.
Next. Yes. No. Right. This time. Okay. So quick thing about me. I'm Simon. I work at University of Bristol in the UK. I'm part of this research group called the Microelectronics Research Group, and we focus on small systems, embedded systems, big systems, high performance computing, supercomputers, and very fine systems and understanding models. That's our main focuses. And we have energy efficiency as our main uniting theme. The thing that everyone in our department is interested in. And myself, I focus on small systems, so embedded systems. Some things I do is I build small systems, I build big systems out of small systems. So I'll show you later. I have a 600 process system built out of tiny devices, and we focus on energy optimization. So there's a project called the MAGEEC project. Jeremy just introduced that, and we'll talk on that later. So these are things I'm not going to cover now, but I'm very interested in. So if you're interested, you can talk to me about them later. So this is the talk I'm going to give. We're going to talk about why I want to measure energy. We're going to talk about energy and power, and how they're related. We're going to talk about measuring power efficiently, and how well we can measure. So what is the accuracy we should aim for if we want to design a measurement system? And then I'm going to introduce our open measurement design, which is available, and we'll download and play with in our workshop, and then we'll wrap up. So let's start with why we want to measure energy at all. Well, why do we care? We care for a bunch of reasons now. Jeremy gave you the idea about power stations being closed, but there's more fundamental things. Most of our electronic devices building now are mobile, distributed devices. They're often run from a battery source or energy company. You have a battery, you have a fixed amount of energy in your system. It's the capacity of the battery. When it has run out, then you have to change the battery or stop computing. So that's a very finite supply. So the more you can make efficient use of that, the longer you can run your computing device for. It comes at a cost. Joe mentioned $1 billion for Google. Well, it comes at a cost even for me. I make a decision about whether to turn my server on and off at night because I can save a good proportion of my electricity bill. But that's not generally made aware to the consumer. And so what we want to do is make it aware to programmers that when they have programming choices, they can see differences in the output of their code and then actively make a choice to produce more energy. So that's about energy. We're also going to talk about power. And devices are now also limited amounts of power. So not just a total amount of energy they can take, but how quickly they're going to display power. And there's some really good reasons for that. There are cooling limitations. So my phone, which I just left at the back there, has a cooling limit of 2.5 watts. If I use any more power than that, I'll burn the hand of the user, and they'll sue me. So this is a design constraint. I can't violate it. I can get past this a little bit, I can drill holes, and then I get about 3 watts, 3.5 watts. After that, I will burn the user again. So that's a real hard limit. That's humans being too weak. We've got battery efficiency. So as you increase the amount of power you take out of the battery, it becomes less efficient. So the total energy available in the system reduces if you take it at a faster rate. And that's chemistry. So we care about power, so we'd like to reduce it. And then there's cost. If I have a system that has a bigger power supply, because I need to take more peak power, the highest power I'm going to take, it will cost me more to build that power supply, and the power supply will be bigger. And that has a cost and miniaturization. So these are really good reasons to worry about both energy and power in everything that we do. So we just get straight the fundamentals here. We have energy, which is this physical quantity that measures the work available to do in the system, or the work that's being done in the system. And that we can relate to the amount of computation that we can perform. So there's some efficiency of computation compared to an amount of energy you put in. And if you said that was fixed, then if you've got more energy, you do more computation. In electronics, the energy goes as heat, and heats up. That's how we lose the energy. So your battery turns into a portable electric heater, and that's what happens in your mobile devices. In wintertime, I put my hands over on this side of my laptop with a nice warm feeling. And that's how we use up the energy. So this is physical quantity, and this is the limit of the mass we'll ever do today, but we'll have a little bit of mass at this level. So we've got energy, E, and we've related to power. So power is the rate of change of energy, and so I can perform this integral. This will turn out to be very useful later when we want to do energy measurement, because what we can do is do power measurement from the integration, and then we get energy. And both have these uses, right? So I've shown you use cases where you need to limit energy, and also where you want to limit power. So that's why it's nice to be able to do both. So to give you an idea about how this works in practice, what you actually do is you make a series of measurements. And so here is a scenario where I make power measurements over time. And what you gain is little thin bars. And there's a reason there's a gap between these bars, and that's that typically what you do is measurement, and there's a rest period when you calibrate the next measurement, and then you read that in. So you get gaps, and you get instantaneous measures. So you don't get the full continuous knowledge. But you get this idea. So you get the idea here is the system is taking a bit of power and then takes less power. And it varies around a bit. You can convert that easily into energy. If you have that set of measurements, you've got a set of power measurements now through time. You can say lots of things about the power consumption of the device. You can also then perform the integration process, which just measures the area under the curve, and now you have energy. So the volume under the curve, the area under the curve is the energy, and the measurements of power. So you get both at once. You just measure the power, and you have everything you need for energy, and more. So energy is typically the ultimate metric that you want to measure when you want to maximize your battery life. And you can say some things that are nice. If you know the amount of energy in your battery, you know the amount of energy your computation takes, you could say things like, well, I have 10 minutes more video time with energy. And that's kind of very useful to a user of the device. You can say, okay, well, you continue watching the film, but you won't get to the end. And then you won't be able to make a phone call either. So that's a choice you can actually make. Say, well, I don't care about a phone call, I wonder what's 10 more minutes on my phone. But there's a big problem in computer science, which is that now we could use many applications that don't terminate. This is all akin to things like APC systems, where you have a big computation, it runs some amount of time, and it ends, and you get results back. But most devices now, embedded devices, just run kind of forever or best effort in a loop. So sensors will never terminate. Little device control my toaster, they never terminate. As long as the toaster is still turned, it's checking the button whether it's been pressed. And so you can't actually measure the total energy of the application, so it never finishes. And we sat around until it heat the So from this point of view, it actually makes more sense in systems to measure the power, since then you get an idea of what's going on right now. And you can, of course, collect the power measurements and say, this is the range I care about, do the integration on the curve I just did, and then you know the system. So the power is the thing we want to measure. So we have the option, we could have measured energy directly, but apparently power turns out to be more generically useful. We can get energy, we can also get more information, and we can do programs that don't tell you. And thankfully it's easier to measure as well, so it's a win-win situation here. So that's what we do, that's what we choose to measure in a modern computing system. We'll measure the power it takes, and then do the maths later. So what we're going to do now is just go a quick bit into the fundamentals of where the energy is going, where the power is being dissipated, and then go on to show how you can measure all this. Any questions so far? Okay, so we're going to just recall a little bit of kind of schoolboy physics. We've got Joule's first law, which says the power of my system is the current of my system, I squared times the resistance of the system. Okay, so if I have current and resistance, I can measure power. And so that suffices to know if I can fix the resistance, which is the thing that I probably want to do in this scenario, then I only have to measure current. I measure one thing, I know one thing, and I can measure the power of the system. The problem is that if you apply this to a computer, the resistance changes. The effective resistance either changes depending on what's happening. So that R is no longer fixed. So I can measure the current potentially, but the resistance I don't know. It'll be different whether I'm doing one instruction to another instruction to whether it's in sleep mode or sleep mode. I can't measure. So one thing we're going to do is we're going to deploy Ohm's law to just rearrange a bunch of these terms in the expression. And what you see here is basically I can rearrange these things any way I like. So I can look for voltage based on the current and the resistance of a system. I can look for resistance based on the over current, and I can start substituting in the various terms of Joule's. So if I combine the two laws together, I can get to this one here, which doesn't require me to know any resistance in my system. So that means that if I could measure the voltage and the current at the same time, then I'll be able to derive the power of that and to know if I do know the resistance, I'm going to measure it. And so this means that you have a choice of how to do measurements, because we can choose which is the easiest thing in a particular scenario to do. And we can get away with measuring one of those. So we're going to come back to that when we show how to build the system. But now we remember resistors, capacitors, and say these are the things fundamentally take the energy of computation. So I'm going to talk about an area called dynamic power dissipation here, which is the thing that isn't just I've got a slab of silicon and I'm warming it up by just having a voltage across it. That's another part of the influence of the circuit. But this is what happens when we do computation. We use these elements and they dissipate. So here's my transistor. This is a modern MOSFET type transistor. The symbol on the left, and this is a very simplified diagram of what it looks like, what it used to look like maybe 20 years ago, but now this will be jagged all over the place due to wonderful plate physics. So we've got two different types of silicon, two dopings of silicon here. And the idea is that this transistor will be able to be switched according to a voltage on the gate here, and if it's switched on, current passes between these two blocks of N-type silicon, and when it's switched off, current's not able to pass through that area called the channel, and this block, and that's how it turns off. So this is a device you can turn on, you can turn off, based on the voltage from the gate. And if you move the voltage from the gate, you will dissipate power. Why? Well, the first thing is, these essentially, if we think of one point of view, the two materials, they're separated together in the arc. So, whenever, well, I've built a capacitor. So this is a lovely parallel structure. That's how our industry has done so well, making these big, mass-produced, very flat devices. So I've got a big parallel structure, so what I've built myself is a parallel plate capacitor. And it's about as long as a transistor. So if I change the voltages at any point in the circuit, I actually start charging and discharging the capacitance system. That's that part of the circuit. So that means that I have to do some work. Let's get going. I've got a slide out. I'm just going to go to the next bit. The other thing that happens here is that we have resistance. It is a semiconductor. The word semi is in there. It's not a great conductor. It has a resistance, an appreciable resistance. And so when I try and turn this thing on, and I pass current between the source and the drain, there's resistance in between. And that resistance is seen in the channel, mainly, and that contributes power. And the reason it contributes power is if we just look back at Ohm's law and Joule's law, we had a voltage across a resistor, that was the channel, and I had a resistance, and therefore it dissipates power. And that power is squared. And this is one reason it's so good to shrink computer chips. Because you shrink computer chips, you can reduce the current going through and reduce the power consumed from one transistor. So that's one effect. The other effect is the capacitance, which I think we can also look at the capacitor here, which is built in the transistor. And the capacitor is related to this equation here. This is the charge, which is essentially the measure of energy, and the capacitor times voltage. So whenever I change the voltage on my transistor, I change the charge in the capacitance structures, and that means that I change the power. And the energy here is just how often I charge and discharge it. So whenever I change the value on a transistor, I dissipate power. Whenever the transistor is on, I dissipate power. So there's a bunch of ways that I can dissipate power. So to give you an idea, here's a circuit. This is a full adder circuit. Everybody recognises it. Just adds together two one-bit numbers and takes it out. So the basic computational circuit you'll find in the heart of any microprocessor. So if red says that this is a high value, so this is a voltage 1, the black one's currently zeros, this is the path of high voltage through my circuit. Okay, so it takes some path between the inputs and the outputs, and it charges up a bunch of transistors in the various gates to which it's attached. So there you go, whang, I've taken some energy. We look at the output there, from that first SAW gate. Once I apply another high input, it changes from red to blue, blue here meaning a low voltage. So the voltage there changed, so it went from there to there, And as it changed, it swung the full voltage of my power supply. Whatever that voltage is, probably 1 volt in one device. And so it charged and discharged a capacitor by a volt. And so we now consume power by that capacitor. So that's the reason that we use the energy. And there's a further effect which is down to, here's an inverter. There's a single input, single output. You get the opposite of what you put in. If you build this device, you build it out of 2 transistors, and you have to arrange transistors in such a way that they are connected together. And when you change the value on this, and only really when you change the value, for a moment you turn on both of your transistors, at least partially. When that happens, you actually connect together your power supply momentarily. And that's a short circuit, and that dissipates large amounts of power, but for a very short amount of time. So these are the reasons that we consume power fundamentally in the device. So we can look at what influences the rate of power consumption. So I showed you that with capacitors, in particular, the faster you change the values, the more you'll discharge and charge the capacitor. So if you've got faster clock, for example, you'll be changing values more often. You'll have faster changing of the flipping of the values of wires, and in 1 second you would then do more charge discharging and you dissipate more power. Okay, any questions about this part? Alright, so okay, fine. So we understand all this. How are we going to use it to measure the power of our system? Let's get on with it. Well, we can measure, you saw we measure power with voltage and current at the same time, or resistance and current. You can measure voltages really easily, really easily. You buy a multimeter, couple of euros, bad multimeter, and you can stick it on and you can measure voltage to reasonable accuracy. You buy an expensive multimeter and get really good accuracy. You can buy an oscilloscope off the shelf and you can attach this and measure voltage with really good accuracy. And you do all of these things, but it's fairly clunky and only partially automatable. The strategy we use is to use a thing called the analog digital converter, which is built into a very large number of off-the-shelf devices in the embedded space particularly. And we can make use of ADC to measure voltage for it. So here's the high-level block diagram. So with ADC, this is a block of a microprocessor, like this ARM-based microprocessor we have on here. Atmel Capital, any bin you can think of produces this, FPGAs happen, everything. So you apply a voltage in to an input to the ADC, give it a reference, ground, 0 volts, and it measures that voltage for you. And it gives you out a digital value. And it gives you some resolution. So 12 bits is quite common, resolution. And there you have your number. You now have measured voltage, you've got a digital representation, you can store it in a file. Typically these things work up to about 2.5 volts in an embedded device. And so any voltage up to 2.5 volts, you can just make it out.
Does it consume enough power to affect the measurement, or is it very efficient?
It consumes a huge amount of power. I have a short slide on that later. But the ADC is actually one of the most power-hungry components of any device that you'll find in the market. That's right. So what we do actually with the boards, in the workshop, the open book design, is we separate this out in a separate board. So you have a separate board, but you don't care about the power that board uses.
Is impedance high enough so it's not affecting the results as well?
Is towards the impedance time over the on the reflection. Yes, the impedance is virtually infinite. In fact, when it's measuring, it's infinite because it's disconnected internally. So they have a sample followed by a conversion mechanism. So it's quite good. But yes, they're really powerful. You can see there's a demo I think you might use later where you turn on the ADCs and you can see the energy consumption board. So this is a big disadvantage, but if you have a separate device, then it's okay. It's a great question. One of the problems that we encounter though is that these devices typically work with about 2.5 volts. It seems to be an industry standard. And often your power supplies may be higher voltages. Right? They may be 5 volts, 3 volts, 2 to 40 volts. Who knows? Now, we can actually do some really simple electronics to bring down any higher voltage into that measurement range. And this is the obvious thing to do. The first thing we want to do, we build this structure called a potential divider. It uses 2 resistors, and that allows us to drop a high range of voltages into a smaller range. And it's determined by the equation that's up there, and V out is the voltage in times its ratio of resistors. So if we want to halve the voltage range, so we have 0 to 5 volts, we put two identical resistors in there, we'll get 0 to 2.5 volts out. And then we bring in this range of the ADC. So that's fun, that's nice and easy. And we'll do that when we need to. One of the problems with this design is you get this current flow through the resistors. You basically put another tap between the power supplies. And so you have to account for that. So if this power supply here is a power supply that's something you care about, so the microprocessor you're measuring, then you're actually adding current onto its current. And that means you'll get a false result about the power consumption. It'll be off by the amount of current that goes through that. But thankfully, these are fixed resistors. You pick them off the shelf, and they have values. So you can account for that, but you've just got to remember to adjust your results. Your processor actually takes less current than you thought it did, because you're wasting current in your measurement. And this is the kind of thing that can affect results if you're not careful about it. You've got to remember to do it. There's nothing hard, but if you don't do it, you'll get errors. That is the backup slide. So, that's voltage measurement. Let's talk about current measurement. So current measurement is actually a little harder. In the old days it wasn't harder. When we had all these wonderful machines with moving irons and coils, we measured the flux directly, they were all fantastic, and they measured current directly, and it's nice and easy. But these days we don't use these, we like electronics, and we want things to be more compact or automatable, and these were fairly bulky and not that accurate or anything. So what we do now if we want to measure current, most commonly, is we measure the voltage count, and we use Ohm's law in order to transform the measurement of current into a measurement of voltage in a known resistance, the I squared R relationship. So we use Ohm's law, and what we'll do is we'll place a known resistance across a power supply. So for example here, I've got a microprocessor supply here, there's the main power supply coming out of a battery, and I place a known resistance in that wire. Then what I do is I get a small voltage appears across the resistor based on how much current flows, and I can measure that. But it's a differential thing, so what I have to do is actually pass it through the thing that measures the difference in the voltages rather than the absolute voltages before passing it on to the ADC. And this guy is called a differential amplifier. So it takes the voltage here at the top on the red line, minus the voltage on the blue line, and that's the output. So you don't care whether this is 5 volts or 3 volts, it's only going to be difference across the resistor. It's directly proportional to the current. The problem with this approach is that this resistor, you have to put it into your power supply somewhere. And that's about how you spend a lot of our free time. But it's an invasive mechanism. If it's not already there, which probably won't be, then you've got to insert it. And you've got to pick the right kind of resistance value so that you don't stop circuit working. If you've got a really big resistor in the power supply, you just can't supply enough power to the microprocessor, and the microprocessor will fall over. If you have it too small, you get a very, very small voltage appearing across the resistance. It's very hard to measure. Tiny volt, 0.00 something volts. So you need to select carefully. Here's my guidelines. My standard microprocessor will deal with up to 0.05 volts change in power supply without care. It's normally specified in the data sheet that that's an absolutely fine range to be in. And so, if you want to maintain that as a maximum drop across your power supply, these resistor values, which happen to be exactly the same as the ones on our measurement board, cover this range, which is the range of typical microprocessors. So anything from microprocessor takes microwatts and up to something from taking full amp. And some of the more powerful ARM boards we have taken over that. And so this range, which a resistor gives you the allowed voltage drop, but it is still very small. So what you're now doing is feeding this kind of voltage into the ADC converter in a microprocessor, which has a range of 0 to 2.5 volts. So you're using some tiny, tiny part of that range. What you want to do is to maximize the part of the range that you use, because that gives you more resolution, gives you more points inside the range that you can discriminate. So what we do is we actually amplify in the analog domain the voltages that we see. So we don't just create that differential voltage, we also amplify it at the same time. And the thing that we do is we amplify by a factor of 50, And that then scales up 0.05 volts into 2.5 volts. So we can then cover the exact range that the ADC is sensitive to fully. And that makes it much more useful. So your question then is, how do you build that amplifier, differential amplifier? Well, that's the stuff of kind of electronics engineering students the world over in their first year. You can use this device called an operational amplifier, well known, well tested, it's very easily available off the shelf, and you build exactly this circuit. So you've got 3 connections on the device, so a differential input, it's got an output, and then what you do is you add in this thing called feedback, which gives you, again, an amplification ability. And you can set these resistors, so for 50 times gain, I set this one here to 50,000 ohms, this one to 1,000 ohms, and you can find that textbook with absolutely nothing like that. And then what we do is just take that check resistance part of that power supply. The downside to this is, when I started just thinking, well, shall I build this circuit, so should we make boards based on it? You find out weird things, like the fact you've got 4 resistors here adds more costs to the assembly of your measurement than it does to buy the operational amplifier. And that's because assembly, the robot has to now go and go to 4 more places, and we've got 4 more resistors, and we've got 2 different values, and there's an actual cost to making this. So if you wanted to mass produce this, there's a way forward to that attractive. And it's annoying, breaks our layout, doesn't look so pretty, all sorts of things. So you can actually buy off the shelf dedicated current sense amplifiers. They're designed for this application across the resistor, and they have fixed amplification. And there is indeed one that gives 50 times amplification. We use ones from MAGEEC. They produce a range of these devices with calibratable ranges, and 1 or 4 different inputs, differential inputs. So you can measure it to 4 power supplies at once, and that's what our boards do. And you do all of this, and it's a relatively expensive chip, but it's nice and neat. The devices have this fundamental limit called bandwidth, which says, what is the fastest that I can amplify? What's the fastest signal that I can amplify? And these devices actually have very low bandwidth, and that's because they amplify so high, times. And they go up to about 2 megahertz. And what that means is that you can't measure accurately a signal that's trading faster than 1 million times a second with these devices. You use these devices, there's no point in measuring faster than that, because they don't have a bandwidth that can't amplify and what's necessary.
There's no point in there?
There's not quite no point, there's little point in that, because what you've done is you've created a system where go back to this diagram. So you've got a system here. If this can measure very, very quickly, you've introduced in the middle a weak link.
Okay.
Yeah. So this kind of passes all of the information from the resistor into the ADC because it has this limit. And so the ADC can go faster and faster and faster, but there's no more information to be got. Yes, it's analog. Yes, so it's a function of the transistors that are built into that device. If you drop the amount of amplification, you can push that up. And this is a trade-off. There's a fixed trade-off between how much you want to multiply the voltage of your signal and how quickly you can do that. And so if you drop that down, and that's why there's a range here, because there's a range of amplification between 20 and 100 times. And if you amplify only 20 times, you get 2 megahertz. If you amplify 100 times, you get 1.3 megahertz. So you have to choose that. So you choose where you lose information in the ADC or
So for this boundary, let's say we have some circuitry that operates in fast, higher frequency.
yeah,
And we lose some information, for example, the switch current.
you'll lose. Yes, absolutely, you'll lose that information.
Is that then power that is significant?
So there's a really good question about what information is in this point. One of the things that happens when you pass a benefit is it smooths the signal, kind of fundamentally smooths the signal. So the total, if you were to take an infinite number of samples of the output, you'll get the same representation of the total energy. But what you don't know is the shape of the curve. So you don't know when it went up and when it went down, but you will see the total used. So you lose in the ability to say, well, it was that part of the loop that took a lot of power, or it was that part. You'll just say, my program took this much. And that will still be an accurate answer, but you can't tell where in time.
There is also difference in the actual power usage.
It will measure the power readings will be different, but the integral, the total energy will be the same. So your energy figure is still accurate, but your when it happened is less accurate. And that's something to be really aware of. That also means that you can do maths, you can do statistical correlations over repeating measurements to try and gain more information, because the total is always the same. But that's an annoyance that's worth it weighing. You can buy a more expensive device to push away the limitation and build a more expensive circuit. You can always do this, almost always do it. And the other problems you have with this device is the analog digital converter part has a built-in error, because what you're doing is you're taking a continuous quantity, which is voltage, and you're producing a binary value, which has a fixed number of digits. It's a discretization. So you can have error, and that's almost always half of a bit. So when you take a value out of a measurement, you should always basically discard the least significant bit, or at least average it over multiple cycles, because that will essentially randomly flip, just depending on exactly how your ADC operates. There's a minimum conversion time, so the ADC puts a speed limit into the measurement, and that means you can't measure faster than the ADCs. They themselves display power, so there was a question earlier about that gives bias on the sample, you've got to remember to take that off. And the final one, they generate quite a large amount of data, even a small, quite slow ADC.
Excuse me, how do you have to interpret this decision?
How does it?
Half an LSD, so these significant...
Bit. Listen to bit. So you've got 12-bit representation. The bottom bit is 0 or 1 plus or minus 0.5.
Yeah, I never know that it's capital B.
You're right. Sorry. Yes, at least a bit. Give you an idea, if you've got a device like this going at 1 million samples a second, you generate 12 bits, you have your sample of registered data, and you then can max out a USB 1. One of the problems we have with this device is that embedded devices are typically not great at doing USB, so getting the data off here, even though it does USB 2, it can't max out USB 2, we don't have the ability to get off all the data that we measure from our devices, even though we only measure this chemistry. So that's well worth remembering. So what you can do is you pre-process data, if you've got a processor lying around, you do that as well. But you do want to say, okay, do I have an idea what's important information? Do I need every sample? Helps you design your software. Any more questions?
Do we need to be concerned about the tolerances on the shunt resistor?
Yes. Yes, absolutely. So the power consumption measurement you get is directly correlated to the resistance, direct proportional resistance. So if the resistance changes, then or has a tolerance error, then your measurement is held by that as well. You can of course measure the resistance in a scope or in a multimeter, so you can have it. For this reason, again, shameless plug, in the open source design, we specify some very tight tolerance resistors, 0.5% resistance, so to minimize any differences. So the shunt resistor is something with 0.1 power.
What about
reduce that?
What about non-linearity of the ADC? You take into account as well?
That will be specified in the data sheet, where that happens. Typically, they are internally calculated to produce a linear output when you get the binary representation. But these kind of things depend on the ADC that you use, and you have to read the data sheet. It's always a caveat. So you normally get a linear binary representation, even if it's not a linear response to the ADC itself. Okay, so we've got some other limitations. So everything's not great, right? One of the problems was we had to connect in this shunt resistor into our devices, which means we either need a board that has one, or we have to do some desoldering followed by some soldering. Typically what we have to do is remove one component to make space for soldering some wires, and then add in whatever you took off, plus your shunt resistor. To give you an idea what these kind of things look like, this is a board we have back in our lab. This is a power supply, it's a 1 volt power supply. We've got a chip here, it's a power supply chip, capacitors, there's a switch mode power supply, it's got a inductor in here. Here's the little shunt resistor in this. I've magnified this quite a lot, so it's a really tiny device. But here's a board and it's got two little probe points, and you can put a multimeter in here, or you can put the circuit I've just shown you across these two sockets, and then you will get the main. And so that's nice. The fact that most devices don't have that, so the BeagleBone White doesn't have it. What you have to do is dab hand at soldering, and I think you see this one on the stand if you want to. And in here there was some power supply components that have been removed, replaced by a bunch of wires and a bunch of glue, and then everything is connected in externally. So if you want to do that kind of modification, you need to know which components to take off. Because some if you take it off, it's going to break. Some if you take it off, it won't break. And you need to know where to connect that into. And there's two popular types of power supply, and they have different components. On small, cheap devices, you typically find this thing called a linear power supply. It's good because it's very cheap and very small, but it's pretty inefficient, so it's not used for large devices and get too hot. And those devices use things for switch mode power supplies. That's the kind of power supply you've got for a laptop. It's much more efficient. These things here, depending on what you put in, might be as bad as 20%, 30% efficient. These ones here are normally 98+% efficient. So let's look at the linear one first, simpler of the two. What it does is it says, okay, I've got an input voltage and I've got an output voltage, that's a voltage for the microprocessor, and I'm going to change the difference by just wasting the energy. Okay, so you put in 5 volts, you've got 1 volt, it just wastes 4 volts worth of energy. And it's really a big transistor. So there's a representation, it's a transistor, it changes its value depending on the input voltage you put in there. It's a regulator, and you get out whatever you bought on the package. The package normally specifies 5 volt output, 1 volt output, whatever you get, what you get out. So you get a voltage out here, 5 volts goes in, 1 volt might come out, and then you add in the shunt resistor for your measurement. Well, you drop a little voltage across that, maybe 0.05 volts, and that means your processor actually now sees 0.95 volts instead of the 1 volt it was expecting. The processor will probably still work, but you're not running it at the same condition that you thought you were. You thought you were measuring it for 1 volt performance, and as Jeremy's mentioned in the previous talk, if you drop the voltage, it becomes more efficient. So you've actually helped the energy use of the system by doing the measurement. Again, you've disturbed the system. Now with switch mode power supplies, we can actually get away from that. Because the regulator has this feedback, it can measure the output and adjusts for it. And so there's a massively simplified diagram of a switch mode power supply. But the switch mode power supply is made by having a switch, a transistor, in series with an inductor, and this switch goes up and down really, really quickly to provide power this way, which is then stored temporarily in the inductor. And it looks at the output and says, do I need to connect the power supply again? Do I need to connect it? And if the voltage is too low, it connects the power supply, if the voltage is too high, it stops. And so this thing goes up and down, 100,000 times a second, and there's a measurement point where feedback comes in to decide whether to close the switch. So you put the shunt resistor in. As long as you put the shunt resistor before the feedback, and it can be in either order with the inductor, and in either order with the switch, then you will get feedback that ensures that the voltage across there is adjusted for automatically. So what that would look like in the same example is 5 volts goes in. Oh gosh, my N button and my page down button are in the same place. It's 5 volts in. You'll get 1 volt out if it's a 1 volt power supply. And the reason is because the power supply will increment on the other side of the shunt resistor. Automatically adjust there. So the shunt resistor will be there, that would be 1 volt. Since it's there, it notices that the voltage changes across it. So now you can run your processor at 1 volt, which is potentially what you want correctly. So it's better from the point of view of being able to make a more accurate measurement for the conditions that you want. And then my last thing on this really is how fast can we do this? So we talked a little bit about the amplifier, but there's another part of my system. Once I have a power supply and a resistor and a capacitor, which is at least the input to my processor, but normally also another capacitor to make a nice stable power supply. What I've built is this thing called an RC charging circuit. And they're well known because they take time to charge them down. And they've got this wonderfully simple relationship, which is the amount of time taken to change the voltage on that capacitor, which is your power supply output, is related to R times C. And what that means is at the point where you're coming out of power supply, the voltage can only change so quickly. And it changes a maximum at speed. And so that limits the rate at which the power supply voltage will change. You'll see a change there. Regardless of if the microprocessor suddenly connects together power supplies and says, I want infinite current now, you won't see that for some time on your measurement. You will see it eventually, but you won't see it straight away. And that means that you can then push through values. This is a common linear power supply. If you push through these values, what actually happens is there's a limit to the physics of the connection. It's no longer the amplification. And it turns out that you buy that very popular off-the-shelf part for regulating 5 volt, power supply, you will never see a response more than 1.5 megahertz. That means in the signal you wanted to measure, there wasn't anything more interesting than running at that speed that you can see. So even if you had a 500 megahertz processor, you won't be able to see its power supply changing 500 megahertz because of the damping that the power supply is doing. So this actually means, we've got this other thing on negative to do, it means you need to measure, there's no point measuring faster than 3 megahertz in this scenario, which you won't see, there's no information available. So that's worth bearing in mind, because otherwise you think, well, I just buy a very expensive oscilloscope and I can measure anything I like. You actually can't. You would never be able to measure it at 500 megahertz. What that means for your output, though, is that if you say, okay, here is my processor running at 500 megahertz, running instructions, with that kind of power supply, you'll never be able to resolve closer together than a block of 300 instructions running once. So you won't be able to say that app that takes my energy. You'll be able to say, that block of 300 instructions, no, let's go and have a look at it. And this limits. So if you want better, you've got to re-engineer the entire power supply to the microprocessor for your package. And so whilst this works for a slow device, so if I had a slow device, I can say this instruction is running at 1 megahertz. I can do that. 5 minutes on megahertz to do that. So again, graphically, you'll never get out this kind of level of resolution of saying, it's this line of my assembly code that took the power. But you might be able to say, well, maybe it's that block of code. And maybe it's got that out. So that's what we're looking at with these kind of measurement devices. And I have, I think, 1 minute left to just show you what these designs look like when you scale. If you want to play more with these designs, you have the workshop session. You can come and even take them. So we've got this device, and it's an open source design. Here's the link, you can download it. We use open source CAD software, and you can download the design from the CAD software, generate files and send them out. 4 channels, 6 megasamples a second, so it would measure accurately everything we've seen today. 12 bits resolution, and this is what it looks like. If you zoom into this in my hand, we've got, this is the amplifier in the middle, the biggest part of the device. We've got a big selection of different shift resistors that you can insert by connecting to the board. So you have to do some soldering. All you have to do is connect your power supplies into some pins here. So you have to break the power supply trace on the board, take 2 wires out, and push them into here, here, and here, and then that's it. Then you set some jumpers, little nice red jumpers we've got, and this will then do all of what I've done. It's designed to be carefully controlled. This thing plugs into a cheap ARM evaluation board. Here, that's what, €9 board. You can buy it off the shelf from RS, Farnell, any of your favourite companies, and that then collects the data and has the ADC inside. I think I'll leave it to my last slide. This is what comes out. And you can play again with this in the workshop. We have software that connects to USB, and you can visualize the output of that measurement device on a PC, a laptop, and here we've got the current measurement going through one probe point, voltage measurement, and the power. And what you can see here is we weren't doing anything on the target processor, and then we do things. It shoots up and then it starts flipping around. And that's the block section. So I think with that, I will just skip to the end and say, it's very useful to be able to do this, because now you can say things like, I can say a block of 300 codes on a 5 megahertz processor. Here's my block. That's the block that is taking energy. Let's go and re-engineer that. Got a slow processor. I can say 5 instructions. We've got the open source design. Please download it. Take a free kit away today. You may need to do a little soldering at the level of just breaking a track, soldering one wire, soldering another wire, and then you can put it into our own design. So as simply as possible. We've got hands-on workshops starting at 12. So with that, I'll leave